will thank you all for coming to my talk. The title of this talk is Towards Deepfake Detection Using Anomaly Detection Techniques. And before dwelling into the details of anomaly detection specifically for deepfake detection, I want to start talking about how traditional methods approach the deepfake detection task, and we will be able to see what drawbacks they have and the motivation behind why we want to use anomaly detection for that. So traditional methods, they approach deepfake detection as a binary classification task, which means that given an input image, binary classification-based deepfake detection aims to estimate the label of the input image, and the image can either be real or fake. So state-of-the-art deepfake detection methods learn a classifier, which can be thought of as a function that maps the original input image to a probability between 0 and 1, which is a probability that the image is real. So the way that we train this classifier is given a training data set of images and their corresponding labels. The classifier aims to minimize the binary cross entropy loss, which is given down here. And the probability inside the log is the probability predicted by the model that the input image is real. Such deepfake detection classifier is seen at the bottom. This is the architecture of the Mesonet deepfake detector, which is effectively just a shallow convolutional neural network, which consists of a series of learned convolutional layers, ending with two fully connected layers. And at the end, we have the output probability that lets us decide whether the input image was real or fake. So specifically, we're going to consider face forgery in videos. And the two most common types of face forgery in videos are face replacement and face reenactment. Face replacement is pretty self-explanatory. So we have two images of two different people. And basically, we change the face of the person in the source image by the person in the target image. And we have this new deepfake image. Face reenactment is a much more subtle facial manipulation where we don't actually change the identity of the person in the first image, but we rather try to mimic the facial expression of the person of the target image, and we want to copy that in the person in the source image. Of course, we can have other common types of facial manipulations, and those could include entire face synthesis, so the generation of a fully artificial face that hasn't been seen before. Or we can have attribute manipulation, which could be the removal of glasses that a person wears, or the change of their hairstyle or hair color, and many other things. So one of the most common deepfake detection datasets is called Face Forensic++, and that contains about 1,000 real videos which were downloaded from the internet, and that corresponds to a bit more than 500,000 frames. And we also have 4,000 fake videos, which contain about 1,000 identities of different people, and that is accounts to more than 2 million images. All of those videos are available in different qualities. So we have the original raw uncompressed version. Then we have a high quality version where the original videos are slightly compressed. And then we have a low quality version where the videos have been compressed a lot. And the reason behind doing this is that we want our detector to be robust in all of those different types of compression, because when people usually create deepfakes and they might post it on social media later, they might do some post-processing operations on them that might lower the quality of the videos. So in a real life situation, we would want our detector to be robust to that. And lastly, in this dataset, we have 5 manipulation methods that are introduced. We have deepfakes, face-to-face, phase shifter, face swap, and neural textures. And neural textures and face-to-face are facial reenactment methods, and the rest are face replacement methods. So now we can ask the question, how do state-of-the-art two-class classifier models perform on this dataset, and how does it in comparison to a human observer? Here we can see the state-of-the-art model ExceptionNet, and we can see that it has very good accuracy across all of those deepfake datasets, and it does much better than the human observer. It's important to note here that for every deepfake dataset, for example, the first one, deepfakes, this network is only trained on real images and fake images from specifically the deepfakes dataset, and then tested on images from deepfakes. So we don't have any cross-dataset generalization performance over here. And that's exactly where the problem lies with those methods, because if we look at the generalization performance to unseen deepfakes, so here in this table, we see the performance of ExceptionNet when it's trained only on specific deepfake datasets and then tested on all others. And we can observe that we have very bad generalization performance across the different deepfake datasets. And this is quite a bad thing, because in the real world, we don't really know what kind of deepfakes we're dealing with. So we would ideally want to construct a model that is robust to any type of facial manipulations, so we can use it effectively in the real world. People have tried fixing this in a number of ways. The first one being, the most effective one being using data augmentation techniques to synthesize pseudo deepfakes, and then those are later used to train a binary classifier. But that comes with the disadvantage that by synthesizing those pseudofakes, you make an assumption on how the artifacts of pseudofakes should look like, and that might also hinder, in some cases, the generalization performance. Other people have used lip reading models to learn representations of natural mouth movement, and that can also be used as a cue to distinguish between real and fake videos. And lastly, where our work lies, recently people have started formulating the detection problem as an anomaly detection task, which basically means you effectively try to make use only of real images during training, such that you don't make any assumptions of how the artifacts in the deepfakes look like, and that theoretically should give you the most generalizable detection method. But until now, current anomaly detection methods still use pseudofakes at some point during the training process. So now we can start dwelling into the details of anomaly detection. And here, anomaly detection makes the assumption that our dataset includes a mixture of normal and anomaly points. And the assumption is that the anomaly points are generated by a different process than the normal points. So there's always going to be a way that we can distinguish between the two somehow. And usually anomaly detection, it involves computing an anomaly score for a given data point, and that anomaly score can later then be used to classify the data point as an anomaly or an inlier. Applications of anomaly detection are numerous, and it's in areas such as abnormal event detection, spoofing event detection, and biometrics. And anomaly detection methods include image reconstruction, one-class classification, and density estimation, which is the one that we're going to be focusing on. Effectively, density estimation, it assumes a dataset of only normal points, and what we're trying to do is we build a statistical model that tries to describe the probability distribution of our normal data points, and then at testing, we have an unknown data point, and we test it against our learned probability distribution. And if we see that that data point does not really belong in the distribution, then it will be classified as an anomaly. So specifically, our method is based on what we call differential anomaly detection. And the idea for differential anomaly detection is to extract deep face embeddings from image pairs of the same person and combine them to train an anomaly detection module. So what that means is that we, given an input image, basically we map that input image using like a deep learning model. We map it to a feature vector, so like a d-dimensional vector, and that's going to be our deep face embedding. And the reason why we want to extract that from image pairs of the same person is that we want to learn natural changes that occur between real images of the same subject. So that could be change of head pose, it could be a change of illumination in that natural image. So that's the idea behind it. Whereas unnatural and extreme changes that are not observed in real images will be considered as fakes. So how that looks like in training, if we look at the figure below, we have two trusted images of the same person. Then using a deep convolutional neural network, we extract deep face embeddings from those images, and then we do some sort of feature combination between those vectors, and we use those to train our anomaly detection module. After our anomaly detection module has been trained, Then at testing, we have again, one more trusted image, and now we also have a suspected image that we don't know if it's real or fake. So we extract the deepfake embedding from those two images, we combine them with our feature combination module, and if we pass it through the anomaly detection module, it will classify, hopefully correctly, this combined feature space into an anomaly point or a normal point. Now moving on to our data and experiments, we also used face forensic ++ to extract real and manipulated faces from the real and deepfake videos. And for every video in each dataset, we sampled 40 equally spaced frames in the video, so that accounts to 40,000 images per dataset. Also, instead of just using the base image as an input to our networks, we first did face detection and alignment using another model called multitask cascaded convolutional neural network, which effectively, as we see in this image here, we take the base image, then we detect the face, and then we align it so basically its facial landmarks are more centered in the image. And the reason behind doing that is that when we're dealing with deepfakes, we assume that any artifacts are going to be concentrated in the face, so we don't really care about what's happening in the background of that image. After that, we use a model called ArcFace to extract deepfake embeddings, and ArcFace is a large-scale pre-trained model that has been trained on the task of face recognition. So ArcFace has already learned to extract meaningful deepfake embeddings from facial images. Now, given two face embeddings, A from a reference image and B from a probe image, we consider the future combination of just taking the difference between our two face embeddings. And after doing that, we train a Gaussian mixture model only on pairs of only pristine images. So the Gaussian mixture model assumes that our dataset can be described by a mixture of n multivariate Gaussians. So that's the density estimation part of our model. Then at testing, we construct pairs of trusted images, so only pristine images, and suspected images, which can either be pristine or fake, and we use those for testing. Lastly, the log likelihood of a testing sample is then used as an anomaly score, which means that the lower the log likelihood is, the more likely it is that the input combined features is an anomaly, because it doesn't belong to the learned distribution. So here we can see some of our results compared to some other state-of-the-art methods. So the methods that I highlighted in yellow are other anomaly detection methods, which, however, use pseudo-fakes for their training process. And the ones that I marked in red are the methods, the two classifier methods that we mentioned in the beginning. So we can see that even though our method does not use any fake images during training whatsoever, it achieves very good performance in 3 out of the 5 data sets. But in face-to-face and neural textures, it doesn't do that well. And probably the reason is because those two are facial reenactment methods where the facial artifacts are very small. So probably our model does not do such a good job in detecting those. But nevertheless, our average performance of our method is still on par with other methods such as ANTAG and Mesonet, which is also a 2-class classification model. But other models such as C-able and Exceptionate, they perform much better still. But also for C-able, it's important to note that this model was trained on raw uncompressed images from face forensics. And the rest of the methods they were trained on the slightly compressed version, so the high quality version of the videos. And that makes a difference because when you lower the quality of a video, then you lose some important information that could be contained within that you could leverage to classify that as a deepfake. So our method shows some promising results, but there's still a lot of room in improvement in those 2 specific datasets for sure. Some other results here, we show the learned threshold of our method, and we can see in deepfakes and face swap datasets, our learned threshold can very effectively distinguish between the fake and the real videos, but in face-to-face, the learn threshold does not do such a good job. Here it's important to note that even though our model works with images, and so you compete an anomaly score specifically for images, you can then average for all of the frames contained within a video, you can average over all of the frames, and you can obtain an anomaly score for the entire video. And that's what we are doing here, because that really improves the results of our method. And it's basically, that's what all of the people in the literature do. So in conclusion, classifier models do not generalize that well to unseen deepfake datasets, as we saw previously. So on that front, people have started constructing pseudo deepfake-based methods, which generalize better, but they still make assumptions about the artifacts contained within the deepfakes. So in order to address that, we introduce a differential anomaly detection module that uses only real images during training, and it provides promising results on face forensics. However, it has low performance on the facial reenactment datasets, face-to-face and neural textures. So what we could do as a future work to improve those results is we could extract more frames from the face forensic videos, because right now we're using only 40. But all of the videos can contain up to 450 frames, so we're only using a fraction of the available frames in the video. We can also try out different feature combinations between the two image embeddings, because right now we're just taking the difference between them. We can also use encodings from the frequency domain, which basically is, if we have an image, we can use a discrete Fourier transform on it and shift it towards the frequency domain. And research has shown that artifacts associated with deepfakes are more visible in the frequency domain than in the spatial domain. Also, we could use information from optical flow, which is a way of measuring the inter-frame dissimilarities between two adjacent frames, which we assume that there's going to be more dissimilarity between two frames of a deepfake manipulated video than a real video. And lastly, we could test our method in other datasets as well, such as the CelebDF dataset, which is a large-scale dataset that contains manipulated faces of celebrities, and it's a bit more involved than face forensics. So yeah, that's everything. Thank you for listening. Have any questions?